Hi, Mr. Sapone here, and we're going to finish our periodic trend screencast. This is the second video, so hopefully you watched the first video, which explained nuclear charge and electron shielding in terms of Coulomb's law. So now we're going to look at periodic trends in atomic size, ionization energy, electronegativity, and reactivity, and we'll define all of these things in the process. So these are the trends we saw in the previous video. As you go across and down a periodic table, nuclear charge increases, the pull of the nucleus gets stronger both ways. There's more protons, there's more charge, more attraction. As you go across the periodic table, electron shielding remains constant. We didn't get additional energy levels as we went across. But as you go down the periodic table, each row represents a new energy level. So electron shielding, the electrical repulsion between electrons, increased as you go down. And let's kind of just look at this picture. We saw this in the last slide, and I kind of ask you what happens to the atomic size of an atom as you go down the periodic table. Well, just generally look at it. Each row you go down, you get another energy level. The atom's getting bigger and bigger. So as you go down a periodic table, atomic size is going to increase because there are additional energy levels. As you go across the periodic table, and this is a little bit tricky because you might think, well, you're adding more protons, you're adding more electrons, you're adding more neutrons, there's more particles. Obviously, you probably need more room for them. It's not true at all. As you go across the periodic table, the atomic size decreases. The atom gets smaller and smaller. Why? The pull of the nucleus is getting stronger and stronger. +3, +4, +5. But there's no additional electron shielding. There's no extra electron repulsion. So the nucleus is able to pull those electrons tighter and tighter and tighter because the pull of the nucleus is getting stronger, but the resistance of the electrons is staying the same. So the atoms get smaller going across. And we can see a pictorial representation of this. And it is really hard to measure the size of an atom, so don't think this is easy. There's actually a couple different methods. They basically just line up two atoms and you measure the distance between them and kind of get a radius and figure out the size from there. But remember, electrons are always moving around or losing and gaining. It's a very complicated process. But as we see here, atomic size increases going down, decreases, atoms get smaller going over. That's the general trend. And that's explainable in terms of Coulomb's law, shielding, and nuclear charge. And here's another graphic you might often see. You'll definitely see it in my class. And it's showing what we just saw with those circles. Kind of make note of all of these peaks. What do these have in common? Well, they're all elements in column 1A going down. Hydrogen, lithium, sodium, and that's terribly drawn. But in the general gist is all of these elements are elements in column 1A. And what happens to size as you go down the periodic table? It gets bigger because there's more and more energy levels with each jump. What happens as you go across the periodic table? Lithium to beryllium to boron to carbon to nitrogen, oxygen to fluorine to neon. As you go across the periodic table, atoms are getting smaller and smaller and smaller. This is plotting atomic size versus atomic number. So each one of these dots is an atom. Hydrogen, helium, they go in order. Lithium, beryllium. So each one of these lines down represents a row on the periodic table. Each one of these is a new row. And there are a few exceptions to the rule, but it's just showing size trends, periodicity, repeating pattern every row that you go across. So we now labeled our size trends. We now have 3. Nuclear charge increases that way, shielding. Atomic size, atoms get smaller going that way, atoms get bigger going down. So we're going to keep filling this thing in. Now we're going to look at ionization energy. Ionization energy is the energy required to remove the outermost electron. That's first ionization, the outermost electron. So right now this nucleus has a charge of +11, and it's pulling on this electron. It's pulling on all of these electrons. It's pulling them in. Opposites attract. There's electrical repulsion. These electrons are repulsing it. But still, the nucleus is holding this electron here. So if somebody were to try to pull this electron off, or another atom or element, it's going to take a certain amount of force. And ionization energy is a measure of that force. It's how much energy it would take you to pull this electron away. So what's going to happen to ionization energy as we go down the periodic table? Well, As you go down the periodic table, we're getting more energy levels. So there's going to be additional electron shielding. And also notice that this electron right here is much further from the nucleus than this one. And Coulomb's law says that the electrostatic force is proportional to distance, and not just distance, but 1 over distance squared. So as an electron is getting further from the nucleus, it's not being held very tightly by the nucleus. The pull of the nucleus is getting weaker and weaker and weaker with distance, and you have more electrons in here that are repulsing it. So as you go down the periodic table, ionization energy decreases. And what that means is it's much easier to remove an electron as you go down the periodic table. What happens as you go across the periodic table? Well, first, ionization energy is going to increase. Because as you go across the periodic table, nuclear charge is increasing. The pull of the nucleus is increasing and increasing. It's getting stronger and stronger. But these electrons aren't getting any further away. There's no additional shielding. So it makes it removing this electrons more difficult because the nucleus is getting stronger and stronger and holding it more tightly. The nucleus gets stronger going down as well, but there's more shielding and there's increased distance from the nucleus. So it's counterbalanced by that. And here's an interesting graphic we sometimes see, and sometimes it confuses people. We have our trends: hydrogen, helium, lithium. Some people often wonder, why do these things exist? Beryllium, boron, and I'll explain why. And let's kind of just draw the electron configuration of some atoms. Hydrogen, we draw an up arrow. Helium, lithium, beryllium, and this is beryllium right here. And we see this little jump because we're going from kind of a filled subshell to a not so filled subshell. We're going to a P with 1 in it. Then we're drawing another one. And then we're drawing another one. And what we have here is now we have the 2p with 3 electrons with identical spins. And as we go down, we have to have an electron with the opposite spin. So this might be a little confusing for some of you, but if you remember electron configurations in doing this, these little jumps are going to correspond to slight changes in electron configurations and how they're going there. So just a little FYI there. So we have our trends. We're adding to our trends. As you go across, ionization energy increases. It becomes much harder to remove an electron as you go across the periodic table. As you go down, it becomes much easier to remove the outermost electron because shielding is increasing and the distance from the nucleus is increasing. Electronegativity is a measure of an atom or a group of atoms' tendency to attract electrons. So electronegativity is going to basically tell us if you had a free-floating electron over here, how likely is it for this atom or this sodium atom to basically pull in and capture this electron? That's electronegativity. How attractive is this atom going to be for electrons? And let's kind of talk about trends in electronegativity in terms of electron shielding and nuclear charge. As you go down the periodic table, electronegativity decreases. Why? We have additional electron shielding and increased distance from the nucleus. If you wanted to grab an electron right here compared to here, well, if you're going to grab an electron here, you're very far from the nucleus. So the force of the pull of the nucleus is going to be much weaker. Even though there is a plus 11, distance is more important than charge. And we also have to look at all the additional electron shielding. All these electrons are going to be repulsing this. So in general, electronegativity is going to decrease as you go down. And as we go across the periodic table again, we have increase in nuclear charge, plus 3, plus 4, plus 5. The pull of the nucleus is getting stronger. There isn't any additional electron shielding. The distance to the nucleus is not changing. This means as you go across the periodic table, these elements can attract electrons easier. They can attract electrons. They can pull them in and snap and basically capture free roaming electrons. And it gets easier as you go across. And here we just see a general chart of electronegativity. And we don't have to worry too much about these numbers right now. But in terms of attracting electrons, fluorine is the strongest. And that makes sense because chlorine's going to have an additional energy level. This would be fluorine. Chlorine would have another energy level. Bromine would have another one. And as we go further over in this whole row, fluorine has the most or the highest nuclear charge of +9. So out of this whole row, it's the strongest in terms of nuclear pull, and out of this whole column, it's more conducive to capturing electrons because it has the least number of energy levels. So fluorine is actually the most reactive element on the periodic table. And this is the reason why. Electron shielding remains constant going across, but the pull of the nucleus, nuclear force, gets stronger going across. And of course, noble gases are omitted because they are inert. They generally don't react with other elements because they have a stable electron configuration. So now we have 5 trends in total, and we're just kind of keeping track. Electronegativity is increasing this way. Ionization energy increasing. Electronegativity is decreasing downward. And the last thing we're going to look at, and I'm going to show you a demo on this with metals and water, is reactivity. For now, we can think of an atom's tendency to lose or gain electrons as its reactivity. So any atoms that lose electrons very easily or have a strong affinity or strong attractiveness for electrons, we're going to consider them most reactive. And I'll give you a hint. Metals lose and nonmetals gain. And this makes sense in terms of electronegativity. It increases going across, and these are all nonmetals over here. So these are going to gain electrons. Metals are generally going to lose. And we're going to see trends in this. As you go down, it's going to be more reactive. Metals are going to be more reactive because there's more energy levels. And I guess, yeah, we can think of it like that. As you go over, elements over there are going to want to gain electrons. These elements are going to want to gain electrons over here. And obviously fluorine is going to be the most reactive in terms of gaining electrons because it has the highest electronegativity. So for nonmetals, the trend is, as the other side shows, it's different from metals and nonmetals. Nonmetals, reactivity increases. As you go this way, these elements are getting more reactive. They're more likely to snatch electrons because nuclear charge is increasing. As you go down, reactivity is going to get weaker. Again, you have more shielding. So chlorine's not really going to be able to grab electrons as efficiently as fluorine, though chlorine is also very reactive. Bromine as well. But again, fluorine is going to be the most reactive because it has the least number of energy levels. And as you go down, metals do the exact opposite. They're not snatching electrons. They're losing electrons. And as you go down, the increased energy levels are going to make losing electrons easier because those electrons in those outer energy levels are very, very loosely held. They're very far from the nucleus, and there's a lot of electron shielding. So for metals, as you go down, they're going to become more reactive. And for metals, as you go across, reactivity is going to decrease. So the trends are different for nonmetals and metals, and the main reason is metals lose electrons, so that extra shielding is helpful. Nonmetals gain electrons, so the extra pull of the nucleus is more important for them, and the lack of extra energy levels going across. And now you have an assignment. 2 questions here. The PowerPoint is also online, so you can read these and kind of answer them. And of course, this will be your essay question on your test, worth probably about 25%. And I'll count it as a quiz grade here. I really like Coulomb's law and shielding and nuclear charge, so hopefully you do a good job with this, and hopefully you have a decent understanding of periodic trends and why they happen in terms of Coulomb's law, electron shielding, and nuclear charge. This is Mr. Sapone. I'm out.